Ok. Grazie, Alessio. Okay, so today we start with a discussion of the basic concepts regarding low temperature detectors. Okay, some wording. What do we mean by low temperature in this field? Okay, if you here you can see how we can achieve different temperatures below the room temperature, and technologies are that we use cryogenic liquids when we want to cool down something at say 100 Kelvin, for example. We can use either liquid nitrogen or liquid argon, as it is done for legend diodes. If we want to achieve even lower temperature, we can use liquid helium at 4.2 Kelvin. If we want to go below, we can pump the helium gas over the liquid, and in that way we can achieve 1 Kelvin. And in the more recent years, there are technologies that allows you to achieve this temperature without using liquids. This is very useful, especially if you have safety issues. And the technology is that of pulse tubes. So with pulse tube, you can achieve a very high cooling power down to temperature of about 1 Kelvin. When you want to go below, you need to do something more technologically difficult, that is to use, for example, a helium-free, helium-4 refrigerator that is able to achieve temperatures down to 10 millikelvin. And that is the temperature at which large mass low temperature detectors that are used for particle detection work. So a bit of wording also from the point of view of detectors. This kind of detectors, from the point of view of history, starts with what are called the bolometers. And this word was used not for particle detectors, but for detectors able to measure the flux of particles. So they measure a power. So the thermal dissipation inside the volume due to a flux of particles or of photons, and have been used and are still used in astrophysics for X-ray, infrared, cosmic microwave, and so on. And this is the field where the bolometer word is mainly used. Then, say in the 90s, we started discussing of the possibility of using a similar technique for a single particle measurement, therefore to detect a single particle. And sometimes we use the same word. We call this kind of detectors bolometers, or we use words like cryogenic calorimeters, low temperature phonon detectors, and a lot of other possible reshuffling of all these words. I mean, the big difference is that what we are discussing today are detectors that are able to see a single particle. And I will discuss mainly large mass detectors, therefore detectors that have the size of hundreds of grams or are even larger, while there are also microbolometers that are able to detect a single particle that are used, for example, for neutrino mass measurement. And one of the differences between these two kind of detectors is that when you have a very small detector, thermal detector of a single particle, you can operate it, say, at about 100 millikelvin. That is much easier. While if you want to operate a detector that has the mass of 100 or even 1 kilogram, 100 of gram or 1 kilogram, you need to go lower in temperature, therefore at about 10 millikelvin. So why we decided to move to a technology that is so challenging from the point of view of the infrastructure, because it requires a dilution, what we call a dilution refrigerator, helium-3, helium-4 refrigerator. So let's look at the main difference between the standard technology that we use for particle detection, that is mainly based on ionization, and the technology that we use when we adopt the thermal readout of a detector. Allora, in the first case, you have that ionization is the primary mechanism of producing the signal. And you produce a number of, let's say, energy carriers or signal carriers, as you prefer, that depending on the specific of the technology requires a different amount of energy to be produced. For example, in the semiconductor, you need about 3 electron volts to produce a whole electron pair. If you move to a technology based on gases, you need 30 electron volt, and if you are using a scintillation mechanism, typically an inorganic crystal, you need about 100 electron volt. And on the basis of this, the energy deposited by the particle and on the energy that is required to produce the signal carrier, you know how many events you are producing, and your energy resolution is limited intrinsically by the statistical fluctuation of the carriers that you have produced. If I consider the thermal detector, the basic idea is that I have a very ideal calorimeter, the one that you study in thermodynamics. So when a particle interacts in what we will call the absorber, releases energy, and at the end, thermodynamics tells us that independently on the starting mechanism with which you have released the energy, at the end it becomes heat, and this heat increases the temperature of your absorber. From the quantum mechanics point of view, this heat is a kind of a vibration of the atoms that in your solid, and vibration they are collective motion, and they are quantized, and the elementary carrier is called a phonon, and its energy is lower than 10 millielectron volt. Okay? So this energy is quite smaller than the energy that we are discussing here. For the same amount of energy released by the particle in our ionization detector or in our thermal detector, we have a number of carriers, signal carriers, that is completely different. So keeping in mind that statistical fluctuation scale with the inverse of the square root of the number of carriers. These are statistical fluctuation normalized to the energy deposited. If you take a semiconductor, that is the best solution when concerning in among ionization detector. For a free MEV signal, you get a resolution of, say, 3 keV, or if you prefer, 1 per mil energy resolution. And this is only the intrinsic energy resolution that is can be achieved using this mechanism of signal production. While if I use a thermal detector with the same kind of evaluation, and assuming that my carrier is an energy of 10 millielectron volt, that is quite pessimistic, and I will tell you why. The energy resolution is 200 electron volt, so 1 order of magnitude lower. Sorry? N is the number of carriers that you are producing. So is the amount of energy that you have deposited inside your detector divided by the energy that is needed to produce a carrier. So in this case, it is 3 MeV divided, this example use a semiconductor, therefore is 3 eV. So the number of carriers is 10 to the 6, okay, is 3 MeV over 3 electron volt, okay? While in this other case, I used the 10 millielectron volt. Can you speak louder? Yes, of course, the amount of energy that is released inside yes, of course, this is a comparison assuming that the particle deposit the same amount of energy. But if you, I mean, when you're comparing solid materials, generally the amount of energy that is released in a particle at the end is very similar if the density of the material is similar. So yes, of course there is a difference, but if you want, you can consider, for example, germanium, okay? Germanium can be used either as a ionization detector because it is a semiconductor, but it works also as a thermal detector. So you can compare exactly the same kind of solid. You will have exactly the same energy deposition when a particle crosses the volume. Of course, you need to have exactly the same volume. And the main difference is that the mechanism that produce the signal carrier is completely different, okay? So this exercise on the energy resolution is really naive, but can show you how promising is this technique. There are also additional motivation for this, for the development of thermal detectors. One is that if I just take into consideration a solid detector, that is what we will discuss in this lecture. From the point of view of an ionization detector, I have a big limitation. I need to consider a semiconductor or a scintillator. On the other side, in principle, I can use whatever material because I'm just using thermodynamics and I have no other requirement. It is not true, I will show you, but in any case, you have much more flexibility in thermal detectors on the kind of absorbers that you can use. And this is important for double beta decay because yesterday we discussed the following point. our future experiment has to use the source equal detector approach. So I need a detector that is itself the source of the double beta decay, and we have a list of isotopes that are candidate to double beta decay, and not all of them, few of them are semiconductors. With some of them, it's possible to grow a scintillator, a crystal that has scintillation properties. But keep in mind that the scintillator does not have the same energy resolution of a semiconductor like germanium. And we also discussed that energy resolution is an important point. While almost with a lot of those candidates, I can build a thermal detector. And then there is another property that is, sometimes it is an advantage, sometimes it is a disadvantage. If whatever is the kind of mechanism that leads to energy deposition inside this crystal, I measure the energy deposition once it is transformed in heat. This is completely independent on the particle that is releasing energy. This means that in a thermal detector, a particle that, a neutron that releases 1 MeV, an alpha particle that releases 1 MeV, or a photon that releases 1 MeV, produce the same signal. This is not true in an ionization detector. So the points 1 and 2 are extremely relevant for double beta decay searches, while 1 and 3 are extremely relevant for dark matter and the detection of coherent neutrino scattering. Why it's relevant for dark matter? Because in that case, I have to detect a nuclear recoil, and I have a detector that has the same sensitivity to a nuclear recoil as it has to photons. This is not true for an ionization detector. So let's see what is the ideal, a description of the ideal calorimeter, and then we will move toward a real calorimeter. Particle interaction produce an energy release inside the crystal, and typically you have two channels for the energy release. You can have ionization in the material and excitation of a lot of different forms. I can have atomic excitation, but I also can have lattices. If I have a solid, it's a perfect lattice if atoms are organized in a crystal, or in any case, something similar to a lattice also in other kind, in amorphous material. And therefore, I have different kind of excitation. But if I wait a while, what happens? Ionization undergo recombination, and if I can neglect the radiative recombination, all the energy is simply transformed into a different kind of excitation. And then all the kind of excitation, they excite, and what happens? From the thermodynamical point of view, we simply say that all the energy is transformed into heat. And from the quantum mechanical point of view, we can say that all the energy is transformed in vibration of the lattice, of the atoms in the lattice, and therefore in the production of phonons. So let's stick on the thermodynamical model. If I have heat released inside my crystal, I have a temperature increase, and the difference in temperature is proportional to the amount of heat, and therefore on the energy that is released, and inversely proportional to the heat capacity of my absorber. And so if I plot the temperature, what I see is a rising temperature as soon as the particle has produced the energy release. Of course, I say as soon, so this is a step increase. Indeed, it's not exactly, I mean, it has a rise time, but it's very, very short, of the order of nanoseconds or even smaller. So let's see. Now, we have a temperature increase, and now our problem is to read out this temperature increase. So the strategy should be, in order to read out this temperature increase, to be sensitive to this temperature increase, is to maximize the signal. Is what we do for whatever detector. We want to design our detector in order to have the best signal. And to maximize the signal, we have to reduce the heat capacity. So this is the first solution that we have to adopt when we want to build a thermal detector. Choose an absorber that has a very low heat capacity. And you may remember that heat capacity becomes negligible and virtually goes to zero when you have the temperature that goes to zero. Because everything becomes freezed, you do not have any kind of degree of freedom, and therefore the heat capacity becomes negligible. So one solution is of course, not only one solution is to go to low temperature, operate your detector at low temperature, and then choose a material that has a low heat capacity compared to others. And this will be discussed in a while. The second strategy is generally to maximize the signal. I mean, I have to read out a small temperature increase, and as I always, when I have to read out a difference in some observables, I have advantages in maximizing the ratio between the signal and the quantity that is changing. Therefore, the variation in temperature over the temperature. And again, we need to go to low temperatures. This is an example. For example, if you take if you assume to have a MAV energy release in a solid at room temperature, and you use the Dulong and Petit law for the heat capacities, you will see that you have a temperature increase of the order of 10 to the 12, minus 12 Kelvin. That is extremely small, and you understand that there is no way of measuring this kind of increase in temperature, because it is more than 12 order of magnitude higher than the room temperature. Is 10 to the minus 15 order of magnitude higher. So I need to increase the signal, and I need to reduce the temperature also to have a gain on the ratio between the signal and the base temperature. And then I have an additional problem. You see, my single particle has produced a signal like this. I neglected the rise time here because it's very short. But what happens if I have a second particle that deposit energy when I'm here, and I should see a rise, I mean, the temperature will rise again, and again, and again. So I need a mechanism that restores the temperature after the signal. And this is obtained by introducing a thermal conductance of my absorber towards what I call a thermal buff. Therefore, a system that has an infinite heat capacity and can absorb heat without increasing the temperature. Okay, so this is our new design of the detector. I have a thermal buff, and this will be my my refrigerator, my cryostat, with a temperature that will never change, in principle. And then I have a thermal conductance that I call G. And in that case, my rising temperature will be transformed as you see here. After the increase in temperature, I will have a cooling of my absorber back to the starting temperature. And this is the evolution of the signal in time. When we study this kind of, I mean, this system, we generally use the analog with an electrical circuit. In that case, the absorber heat capacity is like the charge capacity in a circuit, and the conductance is the inverse of the resistance in a circuit. So this is what we call an RC circuit. The voltage is has a correspondence here in the temperature. So you see, this is my solution. Again, I have the problem of reducing the heat capacity. And so here you see. Okay, no, I will tell later, but in a case, no, yeah, yes. So the tau, it can be, it depends on the size of the absorber that you are using, but we are discussing of millisecond, 100 of millisecond, and sometimes in the real detector you have 2 taus, so you have a fast one, and fast is 100 millisecond, and a very slow one that can be seconds. So these are very, very slow detectors. It's not true for microcalorimeters, those used for the beta decay studies, for the measurement of the neutrino mass using beta decays, because they are very small, they have a heat capacity that is very small. You can tune the conductance toward the heat bath in order to avoid too long decay time in the signal. But in the case of the thermal detectors of using large absorbers, decay time are quite long. And then the rise time I did not discuss now in detail, because first, it's not easy to predict the time that is required for the energy to be thermalized inside the crystal. We need to rely on models, and it's not easy. But then, because in real detector, you are dominated by other factors that change the rise time. And specifically, we are dominated by the kind of sensor that we use to read out the temperature increase. So the model here is very, very naive. So let's now go through a short summary of heat capacities, because this is what we need to know in order to understand exactly which kind of absorber are suitable to build a low temperature detector. So let's concentrate on crystals. If you have a crystal with a lattice, therefore you have atoms of your molecules that are organized in a lattice. At low temperature, the heat capacity has this contribution that is called the Debye contribution. This is a parameter that is characteristic of your crystal, and it's called the Debye temperature. You can find it on databases. And you see that this contribution scales with the third power of temperature. So it goes down to low temperature in a rather fast way. If you do not have a perfect crystal, you have additional contributions. So you may have polycrystals, glasses, amorphous solid, and whatever. You have extra contribution to the heat capacity. In some case, this contribution can be defined as, with a dependence on the temperature that is more or less linear, and so on. This is a problem that, this contribution we want to avoid. Therefore, the solution that is adopted is always to use a crystal, a real single crystal, okay? Single crystal means that is a crystal with a real perfect lattice, without, almost without any kind of defect in the structure. There is an additional problem that we want to avoid and can spoil the performances of your detector when your crystal is not perfect. There is a kind of, I don't know if I'm able to draw this. There is a kind of deformation of a lattice that is called the dislocation. That means you have, a plane that changes a little bit. This is a very naive way to describe it. The lattice structure. And this, in some way, creates an interface inside your crystal. And you could have different responses of your bolometers when you have a particle that releases energy on one side, or on the other, or on both. It's something that what I'm telling you comes from the experience. We have cooled down crystals. We have that look at as perfect crystals. And when we operated them, we have seen, for example, that the response, the pulses that we are looking belonged to two different families in shape. They had different shapes. And when warming up the cryostat, and we look at that crystal, and we have seen that the dislocation was formed. Because the other point that you need to know is that, thermal cycles can break a crystal, even break or create a dislocation or a deformation of the lattice. It depends on the kind of crystal that you are using. So this is only for the contribution of lattice. Then, if you have free electrons, you have additional degree of freedoms. That means additional contribution to the heat capacity. And this contribution decreases with temperature linearly. So if you have a conductor, its heat capacity will be the sum of the lattice contribution and that of the electron contribution. And you see that at very low temperature, you would have electrons that are dominating. So this is, for example, the behavior of the total heat capacity of copper. You see it decreases. This is the sum of the two contributions, so it decreases, and then at very low temperatures, up is dominated by the linear contribution of electrons. So metals are not good absorber for this kind of detectors. No, this gamma is the electron contribution. This is not, okay. In metals, I was taught by solid state physicists that generally tend to form crystal, single crystal. So maybe this is not exactly a single crystal. This is a plot that I've grabbed from the web. So it was just to give you an example and to so in this example, it is assumed that we have only two contributions. One is the bi contribution, and the other is the electron contribution. And so copper is not a good absorber for our detector. Oh, sorry. When you cool it down, the temperature gradients. Yeah, I mean, yes. I will go back later on this. I have two slides, so just wait for a while, and then if it is not clear, you can ask me again. So then we have superconductors. What happens in superconductors when when there is the transition of your material to the superconducting state, you have this behavior, and then you have a temperature decrease that is exponential. So in principle, superconductors are good material to be used for to be absorbers. However, the main point here is that it's not easy to check that you are quite below the critical temperature. Sometimes the transition requires a lot of time. And then you can, I mean, experimentally what we have seen is that when you have particles that interact in the superconductor, you have to deal with the quasi-particles that are broken. And this implies that you have not ideal behavior of your detectors. And so generally we avoid to use superconductors. And moreover, superconductivity is broken by magnetic field. And therefore, you have to operate your detector using a magnetic shield in order to avoid any kind of interferences that leads your detector to change behavior when you have magnetic fields that are changing around, or when you have the Earth magnetic field that is interfering. And so they are not used. So basically what the real choice is to use a material that is a dielectric or a semiconductor, because when you go at very low temperature, a semiconductor behaves as a dielectric material, because the gap, I mean, a semiconductor is a material where the gap between the valence and the conducting band is of the order of the thermal energy. But when the thermal energy goes very, very low, because you are at low temperature, a semiconductor behaves as a dielectric material. So the strategy is you have to use a crystal, and this crystal has to be a semiconductor and should not have magnetic properties. Okay, these are the slide with the magnetic properties. Because if you have a material that has, yeah. Superconductor, yes, but these are sensors. They are used as sensor, and I will go back on that. This is true, but not as absorbers. Okay, so I mean even what the plot I've shown you is very simplified. So is an absorber, and then I assumed to have a thermometer here. But a thermometer is a sensor that is generally made of a different material. And so, and yes, superconductors are used as sensors. But generally, for the absorber, even in microcalorimeters, you prefer to use, I mean, the sensor is different from the absorber. And the reason is that when you have weird behavior due to quasi-particles that are broken and so on, you lose the proportionality between the energy released and the rise in temperature. And so whenever you want a high energy resolution, you prefer to avoid that. In any case, the prescription that I'm discussing here apply to large mass thermal detectors. I will try to tell you when there is a difference, but for example, when you work with microcalorimeters, some of this solution that here I tell you we have to avoid could be adopted, because the constraints are not much so important. For example, I mean, if I want to have a high energy resolution and 1 kilogram of mass, you understand that the heat capacity has to be very, very low. While if I have 100 of microgram of mass, maybe I can accept, for example, a metal. That happened, for example, with microcalorimeters used for the neutrino mass measurement. So there is a further contribution to the heat capacity that can come from magnetic properties of the materials. When you have a material that has a magnetic dipole in the molecule, in the atom, or due to the spin, you have additional degree of freedom. And what happens is that you have, I mean, in correspondence of the transition where you order your magnetic moment, you have a peak. This is called the Shakti anomaly. The peak position depends on the magnetic field in which your dipole is living. And the peak height depends on the characteristic of material, but again, this is an issue, because even if these peaks are often expected at higher temperature than those at which you operate your absorbers, you get problem in cooling them down. You have to control again, once more, the magnetic field. That means you need to install a magnetic field, a magnetic shield in your cryostat, and so on and so forth. And at the end, also, even if we tested the number of crystals with atoms in the molecule that had magnetic properties, we were never able to operate them in a satisfactory way. So we have a number of constraints on the choice of the absorber. And then how we reach low temperatures? Well, we reach low temperatures using, as I've told you, what we call a dilution refrigerator that is based on a mixture of helium-4 and helium-3. And the reason why you use this mixture is that it has this relationship between the concentration and the temperature that you see here. And in correspondence of the decreasing in the temperature, you can separate this mixture in two phases. These two phases has different latent heat and enthalpy and so on. And what happens is that when you have a separation between the phase in helium-free, highly concentrated in helium-free, and that highly diluted in helium-free, and you remove the helium-free from the diluted phase, you obtain cooling power. At the end, is not very different from what you do in what is done by your fridge. Simply we change the mixture, but at the end you just pump. Helium-free behaves a bit like a gas, and even if it is in a liquid, because helium is superfluid, and so you pump a gas over a liquid and you get refrigeration. However, this requires a fridge that is much more technological than the one you have in your kitchen, because you have a lot of, you have to start from room temperature, and you have first to go down to the temperature here, that is the temperature where you have the phase separation. And therefore, there is, you have different stages of cooling. Between 300 Kelvin and 1 Kelvin, you cool this mixture using these techniques, either cryogenic liquids or pulse tube. And then you operate your engine, and the fuel, the mixture that is pumped out cools the mixture that is injected here. Of course, on Wikipedia you can find a description, a better description of how but there is also a paper written in relation to the Cuore cryostat. So words, technical words that we use. Cryostat and dilution unit are two different objects. The cryostat is the set of nested vessel. This is core cryostat, so it's a custom cryostat that was really a challenge to build. So the cryostat is the set of nested vessels. There are two vacuum chambers in between some of this vessel. One is called the outer vacuum chamber and the other is the inner vacuum chamber. They are made of a material with high conductivity, thermal conductivity. Insulation is obtained with vacuum. You have to be careful because you want to, this is the region where you achieve, you reach 10 millikelvin. The cryostat hosts a pulsed tube to cool the shields at different temperature. So they are called, this nested vessel are called the thermal shields. And when you move from outside to inside, each shield has a lower temperature. And one of the problems is that infrared irradiation from the outer shield warms the inner shield. That is why you cannot have, for example, the detector seeing the outer shield. Otherwise, it is warmed by the infrared emission of the warm or hot shield. And then you have your fridge. The engine of your fridge that is called the dilution unit. That is this gray part here. So the dilution unit provide, is able to cool an amount of material at 10 millikelvin. And the cooling is measured in terms of the cooling power, so the amount of power that can be heat power that can be absorbed at this stage. If I quote the cooling power at 10 millikelvin of my dilution unit, is the amount of power that can absorb without increasing its temperature. So what does increase, what is the cooling power that I need? When I have a mechanical system that is cooled, any vibration of this mechanical system produces heat, and so this heat needs to be absorbed by it's called the cold finger, or technically in the dilution unit is the mixing chamber, the place where you have the two phases of the helium-3 and helium-4 mixture. That is the coldest part of the dilution unit. And so it has to absorb all the vibrational power without increasing the temperature. And then I want to read out my detectors, therefore I will have wires. And any wire that comes down from 300 Kelvin will inject power, thermal power in my system. And it's almost impossible to have a single wire that goes down. You have to thermalize the wires on the different plates here to avoid the injection of thermal power inside. This means that it's not so easy to work with this fridge. It's not like the kitchen fridge. So radiation, power, vibration, wiring, and also electrical dissipation, because I will put some power on my sensors, are a problem that you have to control very well. Then there is another challenge, that is to measure the temperature at 10 millikelvin. how can I measure the temperature that is so low? There are two techniques. One is a relative technique. I use a sensor, but without an absolute calibration that I can provide from using, on the other hand, an absolute thermometer. And there are 3 different techniques, one I did not mention. Let's concentrate on this. There are noise thermometers. Johnson noise depends on the temperature, and this is an absolute thermometer. And the other, you remember the Madame Wu experiment done with cobalt-60? When you cool down cobalt-60 in a magnetic field, you have orientation of the spin, and therefore emission of photons in special directions. So what you do is, I've done it a lot of times in the past, when I was a student working on, not on this cryostat, but on a small test cryostat. We inserted a cobalt-60 source embedded in a ferromagnetic material in the coldest part of the detector in order to measure its temperature. And then here, outside the cryostat, we placed a scintillator and sodium iodide scintillator. And we measured the flux of gamma rays when the cryostat was warm. And then you measure it when you have cooled it down, and you have prediction of the amount of the flux. You can correlate the flux that you measure of your photons with the temperature. That means with the orientation of the spin in the cobalt-60. However, this technique cannot be used when you have really a detector that you want to operate, because this is radioactive. So I cannot place at the bottom of the quarry array a cobalt-60 source. And I cannot remove it, because to remove it, I have to open the cryostat. Therefore, I have to remove all these shields to have access here. And then I have first to warm it up and then to cool it down. And this, in this kind of cryostat, takes months. Sorry. Okay, so now I explained you how we can reach low temperatures and what are the prescription for the choice of the absorber. Let's come back to our model of the thermal detector. When we want to be faster, we always call it bolometer, even if from the point of view of the first use of this word, it's not exactly a bolometer. And then when we describe a model where we do not, we assume that the absorber is itself also the temperature sensor. We call it the model of a monolithic calorimeter. Mainly it doesn't exist, because if you use a sensor as absorber, what happens that it has a bad, I mean, the energy response is not very, very good, and you do not achieve a good energy resolution. So we have when you have the temperature of the bolometer that in principle can be different from the temperature of the thermal bath, but we will go back on that in a while. you have an increase in temperature that is proportional to the energy released and to the heat capacity. And you may wonder what is the intrinsic energy resolution of this device. And the intrinsic energy resolution depends on the fluctuation of you produce phonons or heat that increase your temperature. And you have temperature fluctuations because you have a thermal conductance here. The system of your absorber is not a fully isolated system, so it's not a adiabatical system where you release and therefore you have a temperature fluctuation. From the point of view of energy resolution, the temperature fluctuation transforms in this amount of energy. And if you want to use this evaluation of the fluctuation to evaluate the energy resolution achievable with your detector, you have to take into consideration that you have to transform, to read out the temperature. And therefore, you have to add here a constant that depends, is a parameter that depends on the signal readout. But again, you see that from the point of view of an intrinsic energy resolution, you have a dependence on the temperature, on the heat capacity, but you do not have a dependence on the energy that you are deposited. This is completely different from what happens in a ionization detector. So in principle, you should see in a bolometer an energy resolution that is flat with energy, completely dependent on energy. But this is an ideal calorimeter. So the true is, it is not true. Let's take an example. I have 1 kilogram germanium at 10 millikelvin. As I told you before, when you have, at high temperature, this is a semiconductor. This is the valence and the conduction. They are the valence and conduction bands. At high energy, they are semiconductor because the energy distribution, the Fermi energy distribution of the electrons at that temperature allows some electrons to move from the valence to the conduction band being excited by thermal fluctuation. This is no more true when you decrease the temperature because this distribution is moved down toward the energy distribution of electrons is moved down to the valence band. At zero, it's a perfect, at 0 Kelvin is completely, everything is complete freeze. So if you have a germanium at low temperature, behaves as a dielectric. And this also means that all standard electronics and all standard sensor devices does not work at 10 millikelvin because they are all based on semiconductors, okay? So you have to design a new kind of semiconductors. So the by temperature of germanium is 371 Kelvin. The heat capacity, this is the Debye law in real numbers. This is this N stands for the number of different atoms that are in the molecule. In this case, is just one. So this is the heat capacity of for 1 kilogram. In the case of 1 MeV energy deposition, I converted it into joule, and the rising temperature is of 0.3 millikelvin. But here I am operating at 10 millikelvin, so the delta T over T is quite higher than what we have seen for room temperature. And the intrinsic energy resolution is about, I assumed that this parameter is 1 and is of the order of 48 electron volt. So this exercise was a good motivation to start all this development of thermal detectors. So Do you remember this plot I've shown you yesterday? It's the plot of double beta decay candidates once, I mean, this is already what is called the golden selection. So those candidates that have a high Q value, and we have seen that the high Q value means both high transition probability, because it increases with the phase space increases with the Q value, but also some advantages from the point of view of the background, because you have less background at high energy, less background in your signal, in the region where you look for your signal. Okay, so do you have in mind any detector technology that allows you to realize, I mean, to build a detector with standard detector with one of these isotopes? We need to understand if there is some meaning in developing low temperature detectors for double beta decay. So are there alternatives? So for neodymium, no, I don't know. Well, xenon, yes. Xenon is used in TPC. It has scintillation properties, so it can be used. And then it's not solid. You can, I mean, there are ideas to build, I mean, if you cool down at 10 millikelvin is a solid, okay? So it was tested as a bolometer by Michel Dolinsky many years ago. We tested also other liquids. It's not easy to operate them because technically the transformation of a liquid into a solid crystal at low temperature when you close everything inside your cryostat is not trivial. Keep in mind that we operate all the detectors in vacuum. So the problem is that we pump this vacuum, and if you pump on a liquid, you remove the liquid. So, I mean, there are a lot of difficulties, but in principle it could be done. Tellurium, we discussed it yesterday. Tellurium is a semiconductor, but there are no devices based on tellurium, semiconductor devices, diodes based on tellurium, but they do exist based on cadmium telluride, and there is also a double beta decay experiment I don't know if it is still in operation, in Gran Sasso, Cobra. No, okay. Okay. The problem is that you cannot grow these diodes in large crystals, and so if I remember well, they were cubic centimeter. The size of this detector was cubic centimeter, so you need an array. I mean, to go to 1 ton, you understand that it's a bit difficult. And in any case, the energy resolution was not so good. On the other side, Quora is using tellurium dioxide crystals. They can be as large as 2 kilograms. We are using 750 gram only because when we started the design of the experiment, 2 kilogram crystal were not yet grown by the Chinese producer that provided us the crystals. We tested them later, but it was too late to change the project. But in any case, it's a good absorber for a tellurium, for a bolometer. Cadmium. Oh yes, cadmium is, there are scintillating crystals that are used. And it is cadmium tungstate is a very good scintillator. It is used because it's a high Z scintillator, so it has an efficiency for photons that is higher than sodium iodide, that is the standard, maybe the oldest scintillator. So there are alternative techniques for cadmium. However, I remind you that, at least I think that yesterday I've told you that there are two drawbacks in the use of cadmium that are, no, maybe I didn't tell you, but one is that it has a high cross-section for neutrons, and therefore is a potential background. And the other is that not this isotope, but the isotope 113 is radioactive. And so it is true that once you enrich the cadmium, you will remove most of it, but it's not nice. And then, I mean, we discussed a bit double beta decay experiment, but we never told you, I mean, no one of the experiment that is presently operating with high energy resolution uses an inorganic scintillator. Why? Yeah. Yes, that is the reason. The energy resolution is not that achievable with the germanium detector. And so the problem is that you do not have the advantage of having a very high energy resolution, and you have the disadvantage that scaling is not so easy. So in the past, calcium fluoride crystals were used for the study of this isotope. This isotope has advantages from the point of view of the nuclear models because it is easy to evaluate the nuclear matrix element with the shell model. And so for a while it was really considered from the community, but the problem is that the possibility of enriching it is, I mean, there are techniques, but they are very, very inefficient. So it would be extremely expensive, much more expensive than what you think. Orders of magnitude more than the others. So molybdenum, do you know any kind of traditional detector that uses molybdenum? I don't. And there is a scintillator that we plan there are more than one scintillator that we plan to use for Cupid. One of them we plan to use for Cupid, but they are really poor scintillators. So in that case, the energy resolution, and moreover, they have a light production that is sizable only when you are at low temperature. You may know that scintillator have, I mean, the amount of light that is emitted by scintillator generally increase when you cool it to low temperature, down to the temperature of liquid nitrogen. I mean, you do not need to go to 100 millikelvin or 10 millikelvin. So for this isotope, you can rely on bolometers. Selenium, do you know any detector made of selenium? Selenium is a very good scintillator. with a very high light yield at even at room temperature. The main problem is that it's very difficult to grow crystals, especially single crystals. Therefore, it was used a lot, and still it is used, I think, for alpha detection with scintillators, with very small scintillators. But I mean, as a scintillator detector for particle physics, I think it was never used. We operated it in an experiment at low temperature. It has some weird behavior. The main problem with it, as I told you, is that it's not easy to grow the crystals. It's not reproducible. And because I mean, the compound that is used is zinc selenide. And when you grow it, it is not stoichiometric. I don't know if you know what it is. That means that the molecule is, I mean, the molecule that you would like is to use is this one, but sometimes the proportion is not 1:1. If it is 1:1, is exactly that molecule, and especially if it is fixed, is stoichiometric. But sometimes you have, I don't remember, maybe in excess of this or in excess of this. And so it's clearly visible because you have different colors of the crystals, from yellow to red. And also, it prefers to grow as a glass and not as a crystal. So there are a lot of problems. Germanium, it does work, but there is no reason to operate a bolometer when you have germanium diodes. And then calcium I already discussed. So this is more or less the list that I gave you.
I have a question about the low contaminants bullet point on the last slide, actually. So, of course, we want the detector to be very radio pure, but are the low contaminants just for radio purity, or is it also because of like Linus defects like this?
No, it's not for. I mean, generally, radio purity is when you have to grow a crystal, and you go to your vendor and ask him, okay, what is the purity or the precursor that I have to provide you to grow my very clean crystal? It is order of magnitude less than what I require for radio purity. So that is a chemical purity, and it's completely different from the radio purity. Radio purity can be, our requirements sometimes are, say, 10 to the minus 12 gram per gram, while when you, I mean, for the precursors, you do not need really, even the chemical, you need a good chemical purity as a starting point, but the process of crystal growing separates, segregates impurities. So you don't, the final product is, even from the chemical point of view, is cleaner, more chemically pure than the starting material. And you can ask something 10 to the minus 8 is even gram per gram. So it's not, you are not sensitive to defects at that level, at least in our experience, because of course, there are still behavior that we do not completely understand, but we have never been able to correlate crystal performances with radio purity, unless you see a crystal that is highly radioactive. But if we are discussing of the radio purity that we are using in Cuore or we are using in Cupid, they do not provide any kind of contribution to the heat capacity, at least for what we know. And additionally, what I can tell you is that the radio purity of tellurium dioxide crystals that we purchase in China was already very good when we started. We had problem on the crystal surfaces that were not clean because when you polish them, you use powder that often introduce contaminants, radioactive contaminants, but the bulk was not bad. And they were growing already that crystals for different purposes. It has optical properties that are useful for other, for commercial purposes. So the solution for the absorber is to use a single crystal grown in large dimension because you want to reduce the number of crystals in your array. If you want, you have to operate a 1 ton source, you don't want to use 10 to the 6 crystals. Keep in mind that each crystal is an independent detector with its own sensor, its own readout chain. So 10 to the 6 channels are not acceptable for a cryostat. We want the decay fully contained inside a crystal in order to have all the energies deposition inside it. Therefore, the crystal size can't be too small. This is an additional motivation to have to keep the crystal size as large as possible. And just to give you an idea, in the case of tellurium dioxide crystals, in the case of Cuore crystals, the containment efficiency is 88%. That means that 88% of the decays are fully contained, therefore the 2 electrons remain, deposit their energy and are stopped inside the crystals. While if you move to a smaller crystal, this is decreased, but not so much. And you need to know that the density is 6. So let's come to how is really formed the signal. I will go very fast here. If you have any curiosity, you can ask later. So crystal is a lattice where each atom has a rest positioning corresponding of a periodic potential that is due to the electromagnetic field. You can, in the case of a single dimension, you can use this representation. You have, if you just have 2 atoms, you have a spring and therefore an harmonic potential that, if it is quantized, has different energy level that can be accessible. If you have a linear system, it's something like this, and in a lattice you have something like this. And from the quantum mechanical point of view, this excitation to higher energy levels are represented by a quasi-particle or collective excitation that is called the phonon. There are 2 kinds of phonons depending on the relationship between the frequency and the wave vector. We call it the energy dispersion relation, and can be this type or of the other, depending on how the oscillation take place. And when you have are in thermal equilibrium, you generally have phonons populating the acoustic branch over here. So what happens when you have when we adopt this model to describe signal formation in our crystal? At thermal equilibrium, therefore, when the crystal has this, or the absorber has the same temperature as the thermal bath, you have a thermal distribution of phonons. These are bosons, therefore they follow the Bose-Einstein distribution. When you have an energy release inside the crystal, you first have ionization excitation, but in a while, you have that all this kind of excitation are converted into phonons, but these phonons have high energy, much higher than the thermal phonons. So you can design their energy distribution as you see here. We call them athermal phonons. They can be belong to the optical or to the acoustic high energy branches, and therefore they have high energies. This is a picture that illustrates what happens. You have this cloud of athermal phonons, and during thermalization, optical athermal phonons are transformed in the acoustic branch, and then they are degraded to thermal phonons. So after some time, you have that your peak of phonons is moved toward the thermal distribution, and you achieve thermal equilibrium with a distribution that is corresponding to an increased temperature. The problem here is that you need a model, and so you can find completely different values in the literature, but it has a lot of, to my understanding, you should ask to a solid state physicist, but it has a lot of connection also to the kind of mechanism that are active in your absorbers. Because one way to decrease the, to transform a high energy phonon in a thermal phonon is scattering that can happen, take place on the external surfaces by reflection, or on any kind of defect that you have in the So it then depends on the size of the crystals, of course. So what, in our experience, in large bolometers, you are never dominated by this mechanism. And you expect this mechanism to be between, I don't know, nanoseconds and 1 microseconds at most, I would say. But I think there are not much studies on that. So that is the problem. And the motivation is that if you want to study this mechanism, you need a sensor that is sensitive to this, and then one that is sensitive to this. But whenever you add a sensor to your system, you change also the system. So the model is quite complicated. In any case, what happens is the following, that you may have a kind of monolithic absorber, monolithic bolometer where you are sensitive to athermal phonons, and therefore you can have a very fast signal. You can read out a very fast signal. However, so this is the case in which your sensor is identifies with the absorber. The problem is that often these thermal phonons, in the readout of these thermal phonons, you see a position dependence, and therefore you lose in energy resolution because you have a position dependence, so you have two variables in your signal. One is the position where the energy is deposited, and the other is the amount of the signal that you produce. So they are considered only for special application, for sure not for macro bolometers where you need a crystal absorber that is not identical to the sensor, is different from the sensors. In composite bolometers, what happens is that you have a sensor. The sensor is in thermal connection with your absorber. So the kind of thermal connection defines also the kind of phonons that can be transmitted from the absorber to the sensor. In the case of quarry, we have a thermistor that is glued on the crystal. And what we think, again, at the end, we do not have all the tools that are needed to fully understand the behavior of the detector. But according to our understanding, we read out a signal that is produced by thermal phonons. And this is also because the interface between, we have two different interfaces. One is the absorber toward the glue, then we have the heat capacity of the glue, and then we have the interface between the glue and the thermistor. And to say the truth, we have a further interface inside the thermistor, but because the kind of thermistor that we use have this behavior that is described as a thermal decoupling between the phonons and the electrons inside the semiconductor. So it's a very complicated thermal model. And all these interfaces are for sure help the process of thermalization of phonons. So we think that in our case, we really read out thermal phonons. In other cases, the sensors are, maybe this is in the next slide. Okay, in other cases, the sensors are films deposited on the crystals. And in that case, you have a less important interface, and it is possible that you are transmitting athermal phonons. But still, a lot of groups have experienced the problem of a poor energy resolution when we transmit athermal phonons. And therefore, often the choice is to have an interface that try to, maybe they are not perfectly thermal, but they are in between the phonons that are produced immediately after the excitation and recombination of ions and electrons, and the fully thermalization. So this is a list of possible sensors that I used. If you see that here I have removed my thermometer, and I assumed that on the absorber we have in thermal connection a sensor, and this is a list of sensors. Some of these sensors are used mainly for astrophysical applications. These are the only two that are used for double beta decay at present. And this is used in the case of dark matter and also superconducting tunnel junctions. So I will briefly describe these three sensors. The one that we use in Quarry are semiconductors. This is a really standard technology. The only problem is that you need to dope your semiconductor in a completely different way with respect to what we do for semiconductors that work at room or nitrogen temperature. So we have to achieve what is called the metal insulation transition. So this semiconductor at room temperature behave as a metal. So these devices have resistances at room temperature of few ohm. When I cool down them at 10 millikelvin, they have 100 of mega ohm resistances. And they have a dependence, exponential dependence of the resistance on the temperature. In this way, they are very sensitive to a temperature change. Whenever the temperature of the absorber changes, also the temperature of the sensor changes, and therefore the resistance, of your device is changed. So if I put a voltage on my device, whenever its resistance changes, also the voltage changes, and I see a pulse, an electrical pulse. Main features of this device is that it works on a quite large range. That is, your device will have a large dynamics. And this is very welcome. I would say it's needed in double beta decay because it is true that we don't have, the spectrum is something like this that you expect of counts in your detector, and you want to see a peak in a very small energy region that is as wide as the full width of maximum of your detector, and we are discussing of devices that have kV energy resolution. But I don't want to be blind to this region, nor I want to be blind to this region. Because there are a lot of information that I can use for background reduction, either for active background reduction or for passive background reduction. If I'm able to understand what are the contaminants, or not only the contaminants, but the sources that produce the background, in the next phase of my experiment, I'm able to reduce them. The production of these devices is highly reproducible. Indeed, their doping is done in a nuclear reactor. And also the coupling to the absorber is reproducible and easy. You just have to put some spot of glue on the surface of the crystal. A multi-channel readout is demonstrated and is based on a rather standard low-noise electronics. It is not challenging from the point of view of cryogenics because the electronics can be placed at room temperature. But they are slow. So the rise time is between 10 and 50 milliseconds. Then we have transition edge sensors that are based, use superconductors. So this is an answer for your question. In correspondence to the critical temperature, they have a step increase in the resistance. And you can produce the film with different alloys, and you may be able to tune the position of this in temperature of this transition. The problem, this sensor have a very high sensitivity. They can produce very high signals, but the drawback is that they have a small dynamics because when the rising temperature is too high, they enter, they are outside the transition, and they move to the normal state of the sensor. So they have small dynamics. They have a poor reproducibility. It's not easy to tune the transition for all the sensors in your array of crystals at the same temperature, but the temperature is the temperature of the cryostat. So otherwise, you have to add a heater on each of the crystal, control the heater in order to tune the temperature of the heater. Also, the coupling to the absorber is not easy. It could depend on the kind of absorber, because the interface between your alloy and the surface of the absorber is important, and sometimes the matching is not optimal, and so you have to add something in between. The multi-channel readout is extremely challenging. It's not demonstrated, and the main problem is that while these sensors are high impedance sensors that can be read out with a low standard electronics, in that case you need a squid readout. And squids are expensive. In principle, they can be multiplexed, but this is done only for microcalorimeters that are issues for large mass calorimeters. And finally, these devices have very fast rise time. They have extremely good characteristics to be operated for in the field of dark matter searches. Indeed, there are experiments like CREST that use them, but they do not use multiplexing. So they have one squid for each channel. And squid are expensive, and having squid inside a cryostat is not easy. There are also problems in the wiring and connection, even from the point of view of radioactivity. So it's still a solution that is not, has not the maturity to be used for a large-scale double beta decay experiment. And finally, there is this kind of sensor on which I do not have any kind of experience. They are metallic magnetic calorimeters. I will discuss a bit maybe tomorrow, because there is an experiment in Korea that is, I mean, like Cupid in Italy, will use the same absorber of Cupid, but use this kind of sensor. Again, it is a sensor that has a large dynamic. Is based on the change in magnetization of a material that is in thermal connection with the absorber, but not deposited on the absorber. It has a wide range dynamics, therefore has the same characteristic of a semiconductor thermistor from this point of view. It shares with transition edge sensors the problem of reproducibility, readout, because again is a low impedance device and needs squids for the readout. And the rest time is in between that of semiconductor thermistors and that of transition edge sensors. I think mainly because in that case you cannot, you do not have a film that is on the crystal. On the crystal, you have something that we call a phonon collector. In that case, is made of gold, and then you have a thermal connection to your system. So it's not easy to go. When shall we stop? No. Okay. So I think. Okay, and these are the experiments that have used these devices and these devices, but I will discuss them with you tomorrow. Okay? Any other question?
It's just time for one or two questions, if you want, and then we break for an hour and a half, and we reconvene at 2:45, just like this. But if you have a question or two that you still want to make.
I had a quick question. I think it should be quick. So, I don't know much about helium-free refrigerators, but, and I don't remember exact numbers, but helium-free is really expensive and the world production is limited. So, how much is used by an experiment like Corey for their refrigerator, and is it scalable?
Yeah. Okay. So the answer is if you convince DOE to allow you to purchase the helium-free, you get a much better price. Because helium-free is used, is considered strategical because you can use it to control nuclear proliferation because it's used for neutron detection. That is why its price is controlled by the DOE is the Department of Energy in the United States. And so the amount that we use are a few liters in the cryostat. When you purchase a cryostat, they generally sell you the cryostat without helium-3. We have an amount of helium-3 in Gran Sasso. This is a closed circuit, but sometimes you have leaks. So we had also that problem. But at the end, the price is when you are in collaboration with DOE, as for example in our case we have American collaborators. You generally every year or 2 years the DOE start a survey of all collaborators that are interested to helium-free, and you can purchase it. At the end, the price is less than the price of one crystal of Cupid. No, it's expensive. The problem is that crystals are much more expensive. So no, it's something. The main problem is not exactly the price, but simply to organize the purchase in time for the DOE request. Otherwise, you have to buy it on the market, and then it's more expensive and may take some more time, but again, it's feasible. And then now the technology of dilution refrigerator has a lot of interest for quantum technologies. Therefore, the market is changing a bit.
Okay, not today, perhaps not late, but tomorrow perhaps you can just comment briefly on the fact that on the previous slide and this one, you stressed the difference in response speed, relaxation time, if you want, on this different sensor techniques. How important that is a consideration for the application?
No, yeah. I will discuss this because, as you know, it's a big problem for Cupid due to the pileup of two neutrino decay. Because you remember, just a few words, since yesterday we have drawn this plot a lot of time. So this is the neutrino signal, neutrino-less signal, and this is the two neutrino double beta decay spectrum. And we discussed several times what can be the amount of, say, background coming from the two neutrino double beta decay in the region of interest for the neutrino-less. And I've told you is unless you have a bad energy resolution, it's not a problem. And most experiments with rather not very good energy resolution, to be polite, have are working on isotopes for which the half-life is very long. The half-life of molybdenum 110, that is the isotope that we want to use in Cupid, is quite short. It's 10 to the 18, something 10 to the 18 years. But still we have such a high energy resolution, that means 5 kV or 10 kV, it's the same, that we are not worried by this background is order of magnitude lower than the background from external radioactivity. But since our signal is very short, very slow, it happens that even if we are discussing of a half-life like this, we can see pile-up events due to this two neutrino double beta decay. Nobody believes us when we say something like that, but you can have 2 pile-ups. So if you take 2 signals here, and you assume that they do pile up not like this, but they are really simultaneously emitted, you just have a pulse which is much higher, and with an energy that corresponds to the sum of the 2 energies, and so is a count over here. And when you have a rise time on the scale of 10 milliseconds, this this produces a background rate. The problem is that the background rate we are aiming at is counts per keV. This is the background rate. Our goal for the background rate of 2 neutrino double beta decay. So, it's still a very low background rate, but in a double beta decay experiment, it is important. So while when you have a pulse like this, pulse shape analysis allows to reject it. When the pile-up is on the rise time of the crystal, on the signal, it's much more difficult and sometimes it's not possible.
Okay. Lunch.
Thanks.